Okay, so I have here the ultimate guide for solving work and integration problems. So I'm going to talk about things like pulling ropes, leaking buckets, pumping liquids. I'm going to go through tons of examples in this video to really help you understand it. So I strongly recommend that you get the guided notes for this because you will get way more out of this video if you are writing stuff down while you do it versus just watching me. And I do want to say thank you to my students. So I gave a lecture on this. I feel like it wasn't one of my best lectures, and my students asked me so many great questions that really helped me, I think, come up with a better explanation to this. So I view calculus really as a partnership. So I do want to thank my students so much for all those questions. Okay, so just a quick reminder. So we have a work formula if there's a constant force, which is just this nice F times D, force times distance. And what we're going to be looking at are problems that use a variable force. So that is using an integral with this function f of x dx. Okay, so this f of x, this is a force function, and this can be a couple different things. Sometimes this can be a function that brings, I'll just kind of leave it at that. We'll just say for right now that this can be a couple different things depending on the type of application, and I'll show you some hints. Now, something I want to just mention about force. So force is typically calculated m times g, so that's mass times the acceleration due to gravity. But in our problems, how you calculate force is going to be largely dependent on if you're working with an object or if you're working with volume. So depending on what you're doing in the problem, that's actually what's going to dictate force. So units are going to be an enormous key to figuring out the setup of our problems. So I really want to highlight what units we're kind of working with here. So we have SI units and US customary units. So for force, we could be working with either N for Newton or pounds, LB for pound. So for work, we have joules, which are J, or Newton meter. Joules and Newton meter are the same thing. Or if we're talking US customary, that would be foot pounds. Okay, so for mass, in SI units, we use the kilogram. So for US customary, we use either pounds or slugs. So I think a slug is like 32 pounds, technically. I think the book that we use mostly just uses pounds, which I think is technically an abuse of units, but we're just going to go with it. But if you see anything about slugs, that's why. And then we have the length. So the lengths that we're using are either meters or feet. And then also I want to mention acceleration due to gravity. So that's 9.8 meters squared in SI units, or 32.2 feet meters per second squared if we're talking US customary. Okay, so this little chart is going to be very, very helpful for so many reasons. So I'm going to kind of reference this now and again. So the things that are very important are to notice what we need for force and what we're shooting for with work. These two things are actually what's going to guide how you're going to set up your equation. And if you pay attention to this, you can probably figure out everything that you need to do. All right, one other thing I want to state with a Newton. So a Newton in SI units is meters times kilograms over seconds squared. So I bring this up because depending on how a problem describes the weight of something, you might have to account for gravity. And so when that happens, you're going to end up with something that looks like this, and then you convert it to a Newton. So this is also just a little key thing that I might note if I were you. Okay, so the other thing I want to mention is, like, if we're dealing with volume, then gravity is not usually going to come into play. I've noticed that the problems that deal with volume, they're more clear about using Newtons. So when we talk about when do I have to use gravity, it's probably if we're talking about dealing with an object versus, pumping a liquid where we won't have to deal with gravity. Okay, so one of the keys to this is doing some dimensional analysis. There's different ways that you could have to do dimensional analysis, but this table here is really all the units that we want to be working in. And so we use dimensional analysis to kind of guide us to make sure that we are going the right direction. So if you forgot what dimensional analysis means, I can show you a really quick, easy example. So let's say I want to convert 3 hours to seconds. So the dimensional analysis would be, I would say, well, 1 hour is 60 minutes. So I would multiply like this. And then 1 minute is 60 seconds. And then the dimensional analysis part is that I can say, oh, the hours cancel out and the minutes cancel out. So then I'm just left with this calculation here to get my seconds. So if you don't remember or you don't really know dimensional analysis, check out my review video on that. I will just leave that for another video. Okay, so these work problems really come down to units and using dimensional analysis to get there. So I've got this integral formula, which is really darn general. And so the thing I want to remind you of, I know I'm a broken record on this, but I really think this is the key. So our answers need to end up in joules or Newton meters if we're in SI units, or our answer needs to end up in foot pounds. And so that's what we ultimately need our units in. So these parts here are referring to the length part, so the meter or the foot part of that calculation. So these are typically going to help you get to that. And then this f of x, this is often going to end up being in newtons or pounds. So that's the newton or the pound part of the formula. So all of this needs to work together to get us to the right units. And so if we use dimensional analysis for this, we will get what we need to get. Okay, so just one more guideline I kind of want to make then for these force functions. So a thing I've noticed. So when you're talking about variable force with different objects, you're going to need an equation where f of x just ends up in newtons. So if you have an equation that ends up ultimately in newtons, i.e. Meters times kilograms, sorry, I had to make an adjustment there, meters times kilograms per second squared. If you end up with a function that has this as the units, then you're probably doing the right things. When you have pumps or volume, so I'm going to show you how we think about that. So in this case, the amount of work depends on kind of where you are or where the liquid is that you're pumping. So you're going to end up having a function that's doing something with force, so something probably in newtons. Let's see, I should actually probably change this to an F. So when you're dealing with pumps or volume, you're going to be dealing with something that has a force times a distance, and the distance is going to represent the distance a liquid must travel. Okay, so there's these two different ways we want to approach this. So for objects, we want to have a function that just uses newtons, and then for pumps, we want to have a function that uses force times distance. So just reiterating that. Okay, so now let's talk about objects, and I'm going to show you now how we use units to get us there. So you want to haul a 25-meter length of hanging rope. How much work will it take if the rope weighs 62.4 Newton meters? Okay, so it doesn't really matter like how we're doing this. Let's just pretend that this rope is hanging down and we're just standing above it and we're pulling it up. Okay, so if you think about this, first of all, why is this variable? This varies because what matters is how much rope is left. If you've got a rope hanging down off the side of a building and you're just lifting it up, it's going to be heavier, right, when it's all hanging down at the bottom versus when you've pulled the rope up quite a bit, then it's going to get a lot lighter. So the length of the rope is going to impact, so how much rope is left, right, the length left is going to impact the ultimate kind of weight. Now, I want to point something out. Our book uses the word weighs a lot, and I think this is actually an abuse of the word weighs. So this is more like the density of an object. So when you see these kind of metrics, think of it more as like density, even though they use the word weighs. And I actually don't even worry about, I guess, this word. I'm paying attention to the units. So I notice that this says Newton meters or Newton over meter. So this is an enormous cue of how to set up my function. Okay, so I want to set up this integral. And so we're talking about an object here. So I want to have this function. Ultimately, it just needs to be something in newtons, okay? So let's think about this. Everything we multiply together for this f of x, it ultimately, through the dimensional analysis, needs to end up in n units, or newtons as my units. Okay, so as I build this, I know that this force function is going to use this 0.624, and this actually gives us a lot of hints of how to set this up. So this 0.624 Newton per meter, this already has newtons in it. So sometimes you might have to adjust your object and multiply by the acceleration due to gravity. But this is already in newtons, so if you already have newtons, you don't have to worry about gravity. I'll show you when you do have to worry about gravity in the next example, just so you can see the difference. It's a very subtle difference. Okay, so we're almost there. I just need to write a function then that will just end up in newtons, so I can tell that I'm missing something because this is Newton per meter. So the other piece that is missing then is really, like I said, the weight or the force, whichever way you want to think of it. We kind of abuse the word weight when we talk about this. The force of this rope is totally dependent on how much rope is still hanging. So when the rope is hanging all the way down, it is heavier, and when it comes up, it gets lighter. So we need to now multiply this by how much rope there is. So I'm going to call, I don't know how much rope I've got, so I'm just going to call it X. So we'll call it X meters, and that's X meters of rope. Okay, so check out why this works. Now my meters cancel out, and I'm left with this 0.624 x newtons. It's not times newtons, it's 0.624 x newtons. So this is what I am looking for in this function. I want something that ends up in just newtons. And so now I can integrate. So remember, this part here is what's going to bring in meters. So you can kind of think of this as this part here is newtons times our distance of meters. So I integrate, and so look at how this comes in. This formula now is in newtons, and I'm going to bring the meters into it, so that kind of gets multiplied in. And so when I finish my calculation, now I've got something in Newton meters. So this is what I'm talking about. I try to write a function that ends up in terms of newtons, and then the limits of integration and the dx are what are going to bring the meters in, so that I end up with Newton meters. Boom. Okay, let's do another example now. Oh, and actually, before I do that, I have one other question. So I had a question in class that was super awesome that said, what if I wanted to interpret this as a distance left to haul? So I wrote this as how much rope we have, but what if instead I thought of this as like how much rope is left to haul? So at the beginning, there's 25 meters of rope, and then at the end, there's 0 meters of rope. So it doesn't matter if I plug in x or 25 minus x. Okay, so let's find out. So I'm going to replace that x with 25 minus x. And so if I do the calculation, so I run everything out, and I get still 195 joules. And so I had a great question in class. We were like talking about, why does it have to be x or 25 minus x? So why does this work? This is actually a cute, and I will use the word cute, property of integration. So fun fact for you to share at your next party. Check out the setup. B will be a constant. Okay, so here's the first way I set this integral up, and I'll show it to you one more time. So here's just x. This constant here doesn't really matter, right? Ultimately, I'm just integrating for x, so it doesn't matter if there's a constant here. So I have x versus, in this other way I did it, so I took out the constant, 25 minus x. So same idea, let's just say now for a general number b. So if I go from 0 to b of x or 0 to b of b minus x, look at what happens in both of these calculations. So if I run out this calculation, I get 1/2 x squared from 0 to b. So if I run this out, this just equals 1/2 b squared. Okay, but what about this other calculation? So check this out. If I go through and I integrate this, and then I plug in my limits of integration, just this general b, this comes out to saying b squared minus half b. And what is b squared minus half of b squared? It's still just half b squared. That's why these two things are equal. This always works, as long as, big caveat here, this is a 0, this is a b. So it doesn't matter if you want to think of this as b minus x or x. You might end up preferring to set things up like this when you see where we're going with this. But I want to just state that this was a big debate we had in class, and it doesn't matter. So since these are equivalent, we're good. All right, so let's now go back to this idea. So now you want to haul a 15 meter length of hanging rope, how much work would it take if the rope weighs 0.08 kg per meter? Okay, this is different than the last problem, and this is why I suggest you have the guided notes so that you can read the difference between the two. So in the last problem, I had 0.624 newtons per meter. Now I have kg per meter. Okay, so this is where I'm going to have to make some conversions, okay? So we're going to have some work to do. And that work looks like this. I'm going to take this 0.08 and I'm going to multiply it by the acceleration due to gravity. And then I'm still going to multiply by the amount of length left of the rope. So I want you to notice how the dimensional analysis works here. Because remember, I said I'm just targeting something that ends up in newtons. So when I multiply all of these things together, I get a function that leaves me with kg meters per second squared. So, or meters times kg per second squared. And this is what I told you, right, is a newton. So this is a newton in disguise. So what I'm saying is that if they give you this density and it doesn't mention newtons, then you're going to have to multiply by the gravitational, the acceleration due to gravity. If it has newtons, then you don't have to do that. Because ultimately, as long as you end up with a function that just ends up in newtons, you're good to go. So you're kind of just doing whatever work is required to make that happen. And then as far as like integrating this, it's still the same idea, right? So I could have called this x, or I could have called this 15 minus x. I just integrate this. Once again, this is a function now that's just in newtons. These parts here are what are going to bring in my meters. So after I integrate, I get 88.2 joules or Newton meters. Okay, so now let's talk about a slightly different example. So a bag of sand weighing 160 pounds was lifted at a constant rate. As it rose, sand leaked out at a constant rate. 1/4 of the sand was gone when the bag had been lifted to 20 feet. How much work was done lifting the sand this far? And neglect the weight of the bag and lifting equipment. So we're simplifying all of this, okay? All right, so this is still an object. And now this is an object that's talking about pounds. So if we just refer back to this handy sheet, so pounds is that force unit that I'm trying to use. So I actually already kind of have the force unit. So I don't have to do this whole manipulation, right, to get something in newtons. I've already got it. That's like stated in the problem. So again, that's why this is so helpful, because it kind of helps orient you for how much work you're going to have to do. Okay, so I can see in the statement of the problem, let me get back to it. So I can see in the statement of the problem, we've got pounds here. So that's the unit of force that we wanted. So that's cool. But there's the other issue in this problem of the 1/4 of the sand was gone when the bag had been lifted to 20 feet. Okay, so this is where I'm going to pause for a second, and I want you to think about this, because this is actually technically a rate. So what you want to think about then is how much sand are you losing per feet? And so I want to challenge you to try to set this up on your own. If I'm starting with this and I'm losing this amount, I want you to think about how you might set up a function that is ultimately going to be in our force unit, which is pounds. So it's going to obviously have this, but it's also got to take into account that this is happening over the course of 20 feet. So this has a rate associated with it. Pay attention to the units and then see if you can set up a function for all of this. Again, paying really close attention to the units. Just try something and then hit play when you think you've got it. Okay, so first of all, how much sand was gone? So 1/4 of the sand was gone. So 1/4 of 160, that's 40 pounds that's gone. Okay, so if I've lost 40 pounds of sand over 20 feet, that means 2 pounds per foot is gone, okay? So I need to model that in my integral. So what is happening here is this 160 minus 2x. Okay, so what does x represent? X is going to represent how far we've gone up from 0 to 20 feet. Okay, so why does this function make sense? So remember, my goal was to get something that ends up in pounds, right? So obviously, I need to take the 160 that we started with And I'm going to have to subtract the fact that it's losing sand. So 2 pounds per foot. So there's like clearly going to be some subtraction in here. And this X has to fit in for a variety of reasons. So if I do the dimensional analysis, so just look, this is pounds, and then this here, the feet cross out, and so I'm left with pounds and pounds. So I'm still dealing with the function then that is only left with pounds. So you see how that dimensional analysis like guides you. So now that I've got a function in terms of pounds, boom, I can just plug that in. This is the part that needs to be in pounds. And then as I integrate, this is in pounds, and this part here, so these parts here, the 0 to 20 and the dx, that's referring to feet. And foot-pounds is the ultimate unit I need to get to work, or at the end of the answer. So I can finish my calculation here, and I end up with 2,800 foot-pounds. Okay, so hopefully that kind of clears up how to work with objects. And now I want to pivot to working with pumping liquids, which are the other type of work problem. Okay, so first of all, it does not matter what type of pump we're using. All that matters is that we're talking about pumping out. We're just talking about work. So it doesn't matter the type of pump. And it's actually very important to think about like how something gets pumped out. And it doesn't really matter. You could have a pump sitting at the top or a pump sitting at the bottom. Like what happens is the same. So in this case, I've got a vertical right circular cylindrical tank that measures 20 feet high and 10 feet in diameter. And it's full of milk weighing 64 pounds per foot cube. So how much work does it take to pump the milk to the level of the top of the tank? Okay, so first of all, I want to note that this says 64 pounds per foot cubed. So this is referring to a volume. And we're talking about a tank here, so I'm going to draw it. So it's 20 feet high and 10 feet in diameter. Okay, so the thing about this is we're trying to pump all of this milk out, okay? And the key for volume problems is to think of how this milk is moving out. Because where does the variable force fit into this? Well, what varies is kind of where your milk is. So if I have milk here, I have to do more work to pump it to the top than if I have milk here. So I think it's really good when you're looking and you're analyzing like pumping and volume to think about how this moves is like different slabs, and these different slabs are being pumped up. So a slab is going to depend on, right, so the slab depends on the amount work needed to pump. So think about just takes more work to pump up the pink slab than the blue slab. And we're talking about integration here, so we understand that we want to ultimately make these slabs as small as possible. All right, so I'm going to give you a hint now of how to set things up. So the general calculation for the volume of these slabs, I take the area of the cross section, pi r squared, times whatever my slab thickness is. Okay, so something I think that's very helpful when you're just orienting yourself with this is, so first of all, like when I look at my radius, so this is a fixed radius, right? All the way down, it's a fixed radius. It's always just 5. So I can plug in 5 for r. And then the slab thickness, so I talked about, right, that there are these different slabs and we want to make them as small as possible. So I want to just kind of account in my brain for slab thickness. So I'm going to write delta y just so I don't forget that I've got this slab thickness right now. Okay, so now I want to discuss the units here. So this is r squared, so this is going to end up being feet squared. This is 5 feet squared. And then this delta y here, this is representing also some amount of feet, but we're trying to keep the slab thickness something more generalized, right? We're treating this kind of like that Riemann sum. So ultimately, the units here are feet cubed. All right, so why does that matter? That matters because I need to now weigh that against this 64 pounds per foot cubed. Remember what we're trying to do here. We want a function in terms of the force unit pound. So now I'm going to show you how to set this up. All right, so the general way to set this up is I'm going to have kind of this volume density times whatever my volume is. And notice I just left this delta y here for right now. The thing about pump problems is you have to take account of how far or how much work each slab has to go. And now this is actually really going to matter in how you set this distance up, and I'm going to show you why. So this distance we want to model as 20 minus y. That's going to be the distance for each individual slab, and y is going to be the point where that particular slab is. Okay, so notice now when everything is multiplied together, so this part here, this foot cubed, this all cancels out. So I'm just left with this pounds. And then I know that I've got this distance here. So now I've really got this like foot pounds in this particular formula. So this is just the approach that you want to use for setting up these types of force functions with volume and pumping, okay? So what is my integral? So I want you to watch what happens here. So I'm just going to multiply everything together so that it looks nicer. Okay, so I multiplied the 64 and the 25, so that's 1600, and then I've got the pi. And then I've got the 20 minus y that we talked about, so that's the distance each slab has to go. And then I just put this delta y at the end. Okay, so I think that writing your function out like this is going to help you set up your integral, because now where I have this delta y, I can replace it with what you can see here. So I replace my delta y with this dy, and then I can actually set up my integral. So this is going to represent how much liquid we have. So this is the amount of liquid. And then this part here is going to represent the distance any slab of liquid might have to travel. Now, you might be saying, why can't I just use y? And you could have in this problem, but I think with these types of problems, it's better to model like this, to think about the distance each slab must travel. I think this is a much better way to think about this, and I will show you why in a second. This can really matter depending on the type of problem you have. Okay, so now that I've kind of talked about the general outline now for these pump problems, let's just solve this. So if I go through, you can see all my work here. So the integration part is, you know, whatever. So this comes out to 320,000 foot-pounds. And so again, I just want to say that this setup here, 20 minus y, this is going to be the better setup for pump problems. So let's look at y. Okay. So now I've got a cone, 10 feet tall, 10 feet in diameter. And we're going to say it's filled 5 foot high with kerosene, weighing 51.2 pounds per foot cube. So how much does it take to pump the kerosene to the rim of the tank? Okay, so I think this is going to really clear up a little bit more on the setup. So if this is my tank, so first of all, so this is 10 feet in diameter. So from here to here, so let's say that this is the x-axis and this is the y-axis. So if I wanted to model this now on a graph, this is going to be half of 10 feet. So this is the point 5, 10. And so from this information, let's say this point here is 0, 0, and this is 5, 10. I can figure out that this line here is the equation y equals 2x or x equals 1/2 y. So I can just use algebra to figure that out. Okay, so here's the setup of my conical tank, and then it's filled to the 5 foot mark, okay? So it's not, I said halfway full, it's really not halfway full, it's filled to the halfway mark. Okay, so once again, let me get rid of this statement, halfway full, I shouldn't have that in there. Okay, so we still want to think about like this idea of these different slabs, but now this is not a full tank, okay? This is a tank filled up to this pink line, and these little slabs here are what we're pushing up all the way. So, all right, let's break this down now. So the volume is still found the same. So I still use pi r squared times whatever the slab thickness is. But in this problem, unlike the last one, so in the last problem we had a straight radius all the way down. In this problem, I have a radius that is varying. So if you think about just this distance to this distance, so this is being captured by this line here, this x equals 1/2 y. Okay, so with that in mind, I can refer to that, and I can get, so pi times 1/2 y squared, and then the slab thickness is still going to be delta y, and the units here are foot cubed. Okay, so here is the first part of this to get my volume formula. And I know this is in feet cubed. And now I can take that and multiply that against the weight of the kerosene again, right? So I've got this multiplied. So here's my weight of the kerosene. Here's my new volume formula and compensating for the radius that is changing. The last thing that I need to do, once again, is I need to model the distance that this liquid is traveling, or this fluid is traveling. Okay, so in this case now, this is where this is actually going to really matter. This is getting pumped up, so anywhere from here up to the top, which is 10. So this travels depending on, so the feet cubed cancel out. And so this liquid is traveling some distance 10 minus y, and y is wherever we're sitting at in this set of liquid. So here is the distance the liquid has to travel, but look at my limits of integration. These go from 0 to 5. So this has to do with the amount of liquid that you have, and this has to do with the how far the liquid has to travel. And the rest of this is, good to go. So now I've got this is in my pounds. This is a distance here, and then I can just finish integrating. So I've got, and just to remind you one more time, so that part's the fluid available, and then that part's the distance traveled. Okay, so I can finish this integral. You can pause the video if you want to see it. I'm assuming we just want to know what the setup is at this point. But here's the answer that I get for the setup. Okay, so you can see now why setting up this integral in this certain way is important. So I have one more example, and I do want to suggest that you should try this. I think this is a really great checkpoint just to see if you're understanding. So same type of tank, and we're going to have it filled up to the 8 feet high mark, still with kerosene. So my question is now, how does this problem change if you're pumping the kerosene 5 feet above the top of the tank? Okay, so pause here, try this. Try to replicate this whole argument of building everything up on your own, and then hit play when you think you've got it. If you get stuck, I really encourage you to watch just a little bit of the explanation and hit pause and try to work through as much of this as possible on your own so that you can understand it. Okay, so the volume is still the same calculation, right? So everything's kind of the same as far as how we calculate the volume. The only thing that's going to change this time, so once again, I take the volume times this 51.2. So the thing that's different is that now the distance that this liquid has to travel, it's 10 feet tall and then the 5 feet above. So now this liquid is traveling a distance of 15 minus y, and y is wherever the liquid is. And then the other thing that I want to point out here is, so the amount of liquid is going to go from 0 to 8 because that's the amount of liquid that we have this time. So hopefully now that clears up how the setup of these problems goes and how to think of it. And then of course I can just integrate. And so I'll just tell you that the final answer works out to this. I'm going to skip over the integration because this video is already very long. Okay, and so hopefully now this clears up how to do work problems. I would super appreciate if you watched this and found this helpful, that you like it, and possibly just leave a comment for me if you have other questions, or you can always just send them to me. And thank you so much, guys. So I hope that really clears up this issue and you feel more confident now.